right, thanks a lot. So this talk will be about the induction principle, which is, I guess, the main abstract result that we have. And then tomorrow, David will show in the sixth talk how to leverage this to get the actual Langlands correspondence for GLN and some classical groups. And I guess in terms of the overview I gave in the first lecture, this is roughly steps 5 and 6, or at least the first part of 6. So to start, let me just fix the usual notation. So I fix F, finite extension of QP. I will not write all of this because it's the same as always. G is some quasi-split connected reductive group over F. I fix some Borel and some Whittaker datum psi as before. And throughout this whole talk, I will assume that G is well understood in the sense of what David described yesterday, and that we have this Eisenstein compatibility. Okay, so let me briefly recall the main strategy that we had. So we constructed 4 functors so far. And I think it might help to have them all in one picture once at least through the series. So the one we care about is this L psi. So this goes from D of Bungie to int co of par G. Then, for formal reasons, this guy has a right adjoint R psi. And so how were these constructed? Well, there was another adjunction. There's another functor A psi, which goes from Q co par G to D of Bungie. And this has a right adjoint C psi for formal reasons. So this A psi is the origin of everything, right? So this came out of the spectral action of Fock-Schulze acting on the Whittaker representation. Then C psi is the right adjoint. And then we showed that under the assumptions that I have here, that C psi sends compact guys to coherent ones. And so by formal, just by int extending C psi, I go to L psi. So this is some int extension on the compact objects, and then I form this R psi, right? So in particular, you see that R psi is quite far away from A psi. So in order to say anything useful about it, we need some tools, and that's essentially what this talk will be about. So now let me phrase the goal of this talk, so this induction principle. So we make 2 more assumptions. So the first assumption is for all proper Lebbys, M and G, if I look at the Langlands functor for this Levy, then this is an equivalence. Okay, so that's a very mild assumption because by induction we can always assume this. And so here comes the more serious assumption. So the functor L psi I1 lower Schrick. So this is a functor from smooth representations of G of F to incoherent sheaves on par G. Okay, and now the assumption is that this functor has some nice properties. So the first one is that this sends the Whittaker representation W psi to a line bundle. I also assume that it's conservative on supercuspal representations. I guess compact supercuspal is enough. But, oops, that was the wrong one. Compact supercuspal representations and it sends them to cuspidal sheaves so in the sense of the talks we had on Tuesday, I think. Was it yesterday? No, I think Tuesday. Yeah, by Alexander and Hirohisa. Okay, and I will briefly recall that definition later because I need to use it. Okay, so assume these two things, then we conclude that L psi is an equivalence. Okay, and you'll see the power of this result tomorrow, but I guess it's already clear that this can be quite useful because A is essentially no condition, and B is only a condition about a functor from smooth representations to incoherent sheaves. And we've seen David talk about some functor like that, and or at least partially, and we'll see tomorrow how that can be leveraged to get everything we need. So how do we prove this? So I think I already said this in the first talk. So the proof strategy is in 2 steps under these assumptions. So the proof strategy is the observation that alpha psi is an equivalence. If the following 2 things are satisfied. So the first one is that R psi is fully faithful. And the second one is that alpha psi is conservative. Okay, and the talk will be roughly split in half, where I first show the first one and then I show the second one. So how do we show the first one, that R psi is fully faithful? So this is where this magic functor T psi came in. So let me briefly recall how this functor was defined. I think this has so far only made an appearance in the very first talk. So, so this used this notion of admissible sheaves on the L parameter stack. So let me recall. We call F, which is an incoherent sheaf on par G, admissible if this R-hom from any coherent sheaf to F. So this is a priori some derived QL bar vector space is perfect for all coherent ones. Okay, and I think I mentioned, but I don't really want to go into here now, that this is the same as F being suave in the incoherent six-functor formalism. So it is a very natural finiteness condition that you can consider, even though in practice it looks quite weird. And then let me also recall that there's this duality. The admissible that sends the admissible sheaves on par G to itself, and it's an equivalence. Okay, and the last thing I need for T psi is the subcategory of finite sheaves. So we also introduced this co-par G fin. So this was, so this was the intersection of coherent and admissible sheaves. And there was another description which will be really crucial today. This is all the sheaves in INCO such that F is coherent plus set theoretically supported. on finitely many fibers. This map Q, which went from par G to the coarse moduli space, which I think we call X spec G. Okay. Okay. And then there was this spectral temporization result that told us that spectral temporization told us that if I take an admissible sheaf, if I take a finite sheaf, so this then goes to INTCO, of course. If I apply admissible duality, it goes to INTCO, but this factors through QCO. Oh, sorry. Yeah. Thanks. Okay. And using all of this, then let me now define this functor T of psi. So T of psi was by definition the composition of Verdier duality, then the A of psi inverse, and then admissible duality. Oh, sorry, twisted, I guess. So there was a little Chevalier twist of admissible duality. This is a functor from co par G fin to D of Bungie. Okay. And we introduced this functor because this functor is very explicit, and you will see shortly that this has a very close relation to this R psi. Are there any questions so far?
Is there a formula for your D-admissible?
I mean, well, I mean, it's these suave objects, right? And there's tools how you can compute suave objects. So that's one way you can deal with this. So for example, if you allow yourself these weird right-adjoint functors in INTCO, then it is literally just the internal Hom in INTCO to the upper shriek of the unit in INTCO. But in practice, that's extremely unhelpful. Like INTCO is a 6-functor formalism, right? We mostly talk about only the 3 functors, but they have right adjoints. If you allow those, then the suave duality is just Verdier duality, like you write down the same formula, but now you have these weird functors.
But the resulting right adjoint is something.
It's something strange. I think in practice, what might be more helpful is you have this comparison of coherent duality and Grothendieck-Serre duality and admissible duality. Like if you, I mean, to characterize a sheaf on INTCO, it's enough to understand how to Hom in from any coherent sheaf. But if you take the admissible dual, then Homming into the admissible dual, you can rephrase as Homming out of the Grothendieck-Serre dual of the first guy, and then dualizing the whole thing.
Oh, okay. Oh,
so
that makes it interact well with your definition of admissible.
Yes. That makes it interact very well with this first definition, where it just said that these things are perfect. But also, I mean, these are the suave sheaves. So, and there's, I wrote a whole paper with Claudius on suave sheaves, and there are some tools how you compute with them. So.
In classical geometric Langlands, there is actually a formula relating this analog of this BC duality with the analog of this Verdier duality up to some Eisenstein functors, like this classical complex. So I don't think that's complex. And this presumably gives you a formula relating Grothendieck-Serre duality with this admissible duality up to some Eisenstein functors. That was actually, Linchamp proved this, and it was motivated by Aldo trying to compute with this functor.
Okay, you're saying there's some relation between Grothendieck-Serre duality and admissible duality?
Up to some complex defined by Eisenstein functors, at least classically. I mean,
Okay.
I think it's more, this formula Lucas mentioned is more useful than already appeared in my first talk. To Hom towards an admissible dual is the same as Homming from a Grothendieck-Serre dual and then dualizing the whole thing. So in the paper we use this like 20 times. We call this the duality exchange.
Right. So this is also, by the way, a general paradigm you have in six-functor formalism, like homing from some prim guy to some admissible Slav guy, and then taking duals. Like there's some exchange formula that you can write down. Okay, we can talk about this other thing later. I'm a bit confused by that, but yeah, maybe talk about this after the talk. All right, so we have this weird class of admissible sheaves. And let me also maybe point out that these admissible sheaves they only form an interesting category on stacks. If you go to schemes, it's pretty boring. Like if you have, for example, an affine smooth scheme, then these are exactly the perfect complexes that are supported at finitely many points. So it's a very small thing. And if you have something like proper scheme, proper smooth, then it's exactly the perfect complexes. So it's bigger, but still not that interesting. So it really only becomes very interesting once you pass the stacks. And I think David already mentioned this example. If you take the classifying stack of some algebraic group, then the regular representation is always an example of an admissible sheaf. Just because the push from point to the classifying stack, if your group is smooth, then that is a smooth map. And so it's prim and intco, and so the push preserves smoothness. So that would be one way to say this. Okay. So, any more questions on admissible sheaves? I think we also mentioned that these things can be actually incoherent sheaves. So the fact that the spectral temporization holds is really magical. I think David even wrote down this LO or LE plus like this colimit on this coordinate cross. So that is an actually incoherent admissible sheaf. Okay, so now here comes the crucial reason why we care about this functor T psi. Namely, if I take R psi and I restrict it to these finite sheaves, then this functor agrees with T psi. Okay, so let me sketch this now, why this is true. So there's two steps. The first step is I write down some duality exchange formula for A psi. So suppose I have some perfect sheaf now with quasi-compact support on par G. Then you can show that if I take the Bernstein-Zawlinski dual of A psi of, what happened? Of F, then what you will get is the A psi inverse applied to a twisted Grothendieck-Serre dual of F. Okay, and since F is perfect, this Grothendieck-Serre dual is really, it's really just a dual. So I think, let me just point this out. So this is the same as just a dual of F. So what goes into this proof? So there are two main ingredients that go into this proof. So this follows from duality for the spectral action. So I think this was written down in David's third talk, which looked pretty much like this, but you might be slightly confused why there's a psi and a psi inverse. And this comes from the fact that this A psi was not literally the spectral action. It's the spectral action applied to this W psi, right? And so if you apply these Bernstein-Zawlinski duality to this A psi F, you have to, well, you will see that the Bernstein-Zawlinski dual of W psi appears. And so you have to understand this. And so this is the second statement that you need to know. Namely, if you take this cohomological duality of W psi, so cohomological duality is just Bernstein-Zawlinski duality for representations instead of sheaves on Bungie. And you can restrict this to a single Bernstein block, S. And then you can compute this. So, and this will give you the same for the dual block and the inverse Whittaker datum. And this was, I think, this was proved by David in these Beijing notes. Okay, and now if you combine these two statements, then you will quite easily get this duality result. Okay, and then the second step. So now here comes, well, I'll shorten this by just saying by playing with the junctions. You can deduce from the first one that we get for all sheaves on band G and coherent sheaves on par G that are finite, if I take the R hom from A to T psi F, then you can check that this is the same as the R hom from C psi A to F. Okay, and I looked a while at how we do this, and I did not find a nice way to say this. So it's essentially like 10 to 20 lines of manipulations, but it's pretty much formal. So you just take the input that you have in step 1, and then you start transforming. So in the first step, you plug in the formula for T psi, right? Then you see that there's some VD duality at the end. So this is just some internal hom, so you can pull that to the other side, so you can switch around, and then you just start playing with these formulas. And I will not go into the details, so if you want to see that, I will refer you to, let me maybe use some color here. So this is, I think, theorem 5, 6, 3. So have fun if you like. But let me maybe at least give some intuition why you should believe this to be true. And I think I already said this in the first talk, but like the key intuition is that, so you see this C psi behaves like a left adjoint to T psi, which might confuse you at first a little bit because C psi was defined as the right adjoint of A psi. But now I have these two dualities, and dualities are contravariant functors, and so they change the order of a junction. Okay, so this is why you should believe this statement. It's unfortunately not a proof, because you have to be careful because these functors are defined on various different versions of QCO and INTCO, and that's why this gets quite technical if you actually want to make this work, but that's the intuition. So these dualities, they swap the order of a junction. Okay, so that's why you should suddenly see C psi on the left, even though it's T psi is defined using the left adjoint of C psi.
Why does the Chevrolet evolution come in?
Because it's already, you see it already here, right? And here it comes from the, for the similar result for the spectral action, this duality result. And then ultimately it boils down to if you have a Hacker operator, it's defined on this Hacker stack, on this local Hacker stack, right? And if you want to pass to the dual thing, you have to swap the two legs of your Hacker stack. So there's this L plus G, LG modulo 2 copies of L plus G. You have to swap the two. And if you look at what Satake does to that swapping, it exactly induces this Chevrolet involution. That's ultimately the reason. And then you pass that to tons and tons of commutative diagrams, and at the end you end up with this. Okay. And then, okay, so this last step is just a minor step that I can also put an L psi here. Because F is coherent, and you can check that this R-hom doesn't change. I mean, this L psi is essentially C psi. It's just lifted slightly, right? But this F is coherent and hence bounded, and on the bounded part, this QCO and INTCO don't do the same thing. So this doesn't matter. Okay, but this is really what we wanted, right? Because now we have the L psi on the left, and we have the T psi on the right, and so this proves, because R psi was by definition the right adjoint of alpha psi, we see that t psi is the right adjoint of alpha psi, at least on pi g fin, which is exactly what I wanted to show. Okay, and so now here comes the corollary. So if A psi is fully faithful, then R psi is fully faithful. Okay, and here's again the sketch. So first, so you do this again in 2 steps. So the first step is that A psi fully faithful implies T psi fully faithful. Okay, and that is relatively easy because T psi is essentially just A psi up to 2 dualities. So this follows from the fact that this d-admissible and d-verd are equivalences. And you have to be slightly careful, and we'll just say this orally. You have to be slightly careful, of course, because, okay, the first d-admissible is no problem. This is clearly an equivalence, but then you have this Verdier duality at the end, and that is only an equivalence on admissible sheaves, or UL A sheaves, I guess. So you have to know that the thing that you get is a priori, you need to a priori know that it's UL A, but fortunately, this Verdier duality also detects UL A sheaves, so it's enough to show that the whole composition is UL A. So the whole T psi lands in UL A sheaves, and this fortunately follows quite directly from this adjunction that I just wrote down. Because this adjunction tells you how to hum into this thing, and UL A you can characterize by humming into stuff. I will just say this orally because it's really not that interesting of a point. So more interesting is the second point. So T psi fully faithful implies R psi fully faithful. Okay, so how do we do this? Well, we know that R psi preserves compact objects, so it's enough to check this on compact objects, so coherent sheaves. Unfortunately, T psi is not R psi in all coherent sheaves, only on these finite ones. So we need to do something here. And this is why David told you about these restricted sheaves. I think this is the one place where this comes in. So recall that we had this idempotent co-algebra O-restricted living in QCO of par G. Okay, and by acting by this restricted, we define these restricted subcategories. And so this defined now for int co par G. If I just act by this O restricted, then this will land in the full subcategory of restricted sheaves. And David already mentioned that this is just int of co par G fin. Okay, so this is really crucial to know. And then I can do the same on the other side. I have D of ban G. So I can act by this O restricted, now by the spectral action, and this will get me into something which we call D of ban G restricted. So this is again a full subcategory, and I'll put this in brackets here. You can also check that this is the int category of finite sheaves on ban G. So finite is UL A plus compact. Okay, so you can check this by hand, but I don't really need this, so that's why I put it in brackets. Okay, and then by compatibility, of L psi and R psi with the spectral action, both of these functors commute with restriction. With these restriction functors. Okay, and this is something, so this is where we really need this restricted, because I guess you can by hand write down these restricted subcategories, and it's probably also not hard to show that they have some right-adjoint mapping to it. But then I think for one of the two functors it's probably easy to see that it preserves, that it commutes with it, but for the other one it's really hard. And so there's really some non-trivial step going on here, that the fact that we can write the restriction functor is just acting via the spectral action. This tells us that these functors do commute with the restriction functor. Okay, so this is the only reason we need this restricted thing. Okay, but now we can finish the argument. So now fix some sheaf f in int co par g. Okay, we need to show that the natural map from elf psi, arp psi f to f is an isomorphism. Right? This tells us exactly that arp psi is fully faithful. And then we already know that arp psi preserves compact objects, so we can, without loss of generality, assume that f is actually coherent. And this helps in a second. Okay, and now we use one more property, namely that this restriction functor on coherent sheaves, this tensoring with O restricted is conservative. Okay, and what's the idea behind that? Well, we know what the restricted category looks like. It's just these finite sheaves. And so if you look at what this conservative means, it just means that for any coherent sheaf, I have some non-zero map from some finite sheaf. And that's really believable, right? Because these finite sheaves are exactly those that are coherent and set theoretically supported on the closed fibers over the spectral, the coarse moduli space. But any coherent sheaf will have some non-trivial stalk at some closed point, and that closed point will lie in some closed fiber. And so then some skyscraper sheaf at that thing will be finite and will map non-zero in a non-zero way. Okay, so here you really need to know that these restricted sheaves are exactly these finite ones and have this very explicit description. Okay, and since I know this, and my f is coherent, and my r psi and alpha psi preserve this coherentness, it's enough to show that if I take this alpha psi, r psi, f, and I tensor this with O restricted, it's enough to show that this is an isomorphism. Okay, but now I'm on the restricted subcategory, and here I do have my T psi available. So this now follows from well, I guess I should maybe mention this once. So this is, note that this is the same as alpha psi, arp psi applied to f tensored with this O restricted. Right, so here I use the fact that alpha psi and arp psi commute with this restriction functor. And now this follows from the above proposition, namely that arp psi restricted to this co-par G fin is T psi, and this is fully faithful by assumption. Okay. So, any questions about this? You want me to scroll down or up? Like this? Okay, so morally the idea is just I can control R psi on some small subcategory, and that subcategory is barely large enough so that it allows me to deduce fully faithfulness of the whole functor just from knowing that it's fully faithful in the small subcategory. And the precise way of stating that is using this restricted stuff. Okay. So there are no more questions. So the good news is that if you don't like restricted sheaves and you don't like admissible sheaves and so on, you can forget about them now, because this is the only place where we use this. So this sheaf psi and this restricted stuff and all of this goes into this one proof. This one corollary here. Okay, but this corollary now reduces the checking that R psi is fully faithful to the checking that A psi is fully faithful, which is really nice because A psi is something we can control. All right. Then I will continue with the second step of the induction principle, which is the conservativeness of the functor L psi. So let me briefly recall these cuspidal sheaves that made an appearance there. Okay, so I'll recall two things that I need. So we had these Eisenstein functors on both sides, spectral and geometric. And I will recall one property that I will need in a second, which I think was also in Terehisa's talk, namely, given an element B in B of G, I can let P be the dynamic parabolic of the Newton point, which is some co-character of G, and then let B M and B of M be the induced element. Then the group G I have at this point B is the same as the group, well, for M at this point Bm, and I can write the IB lower Schrick, and there's some small renormalization, and don't worry too much about this. That's just some shift and twist. And I can write this as the Eisenstein functor for P minus composed with just the lower Schrick restriction, but now on Bahn M. Okay, and these are functors from smooth representations, GB of F, which is the same as MBM of F, to D of Bahn G. Okay, and this is very useful, and we will use this in a second. So keep this in mind. And then also it was defined in Terehisa's talk that a sheaf F and int co of par G is cuspidal if I take the spectral constant term functor CT spec chi of F, and I want that to be 0 for all proper parabolics P and G, and all, I think, dominant, right? And all P dominant chi. Okay, and so the idea behind this was this. So remark, So this corresponds to sheaves on bun G that are supported on the basic locus and generated by irreducible supercustomable representations. On these basic B. Okay, and vaguely the reason for this is that you use the adjunction between Eisenstein and constant term, and then you see that if the constant term is 0, this means that there cannot be any maps from Eisenstein functors. And by the thing I wrote above, these Eisenstein functors, they basically give you everything away from the basic locus. Okay, and so now I will use this to prove the induction principle. So finally, or are there any questions so far?
Would you mind scrolling off and reminding us what the induction principle?
I wanted to do that now, yeah, okay. But any questions up to here, I mean. Okay, so, right, so what was the induction principle? So we wanted to show that for, assuming that for all proper Levis, we have an equivalence, a Langlands equivalence, and also this functor L psi I1 lower Schrick has certain properties, namely sends W psi to a line bundle. It's conservative on complex supercuspal representations and sends them to cuspal sheaves in the sense that I just defined. Okay, and then we want to show that L psi is an equivalence. And I guess I'm not good enough with this tablet to just copy this down, so I hope you can remember this because I don't want to write this again. So I'll now put myself in the situation that I have these two properties, and then I will try to prove that L psi is an equivalence. Okay? Okay, so we assume that these conditions A and B of this induction principle. Okay, so the first observation is that, so we assume that, we assume that the C psi of W psi is a line bundle. Oh yeah, sorry. Thanks. So we assume that this C psi of I1 lower Schrick W psi is a line bundle. This implies that A psi is fully faithful. Okay, I think I said that in the first talk. Because A psi and C psi are Q collinear, you only have to, for this fully faithfulness, you only have to check it on the unit, that the adjunction unit is an equivalence on the structure sheaf, and that amounts to showing that a certain map is an isomorphism, and that's a map of algebras, and if both are line bundles, that needs to be an equivalence automatically. So this is pretty formal. And now from the above corollary, this implies that R psi is fully faithful. Okay, so this is the first step. And the fact that this is a line bundle was part of this condition B. And now comes the second step, so it remains to show that L psi is fully faithful, is conservative. So remains to show okay, so what does conservative mean? It means if I plug in something that's non-zero, it will not be non-zero. So how do you show? It will not be zero. Sorry, yes. It will hopefully be non-zero. So we fix something that is non-zero. And because we know that L psi and R psi preserve compact objects, I can restrict to the fact that A is actually compact. Yeah, restrict to this case. Okay, so we need to show that elf psi A is not 0. Okay, and I will sketch the proof. I think I have about 10 minutes left, so let's see how far I can come. So the proof goes in 2 steps, roughly, or two different main ideas. So the first one is, so I know that A is compact, right? So it's only supported at finitely many strata of Bun-G. And so I can fix just one minimal or maximal, like one that does not specialize further in the support. So I fix some point B. Okay, so let list be, I guess, maximal. It's always a bit confusing what your ordering is. But so one that does not specialize further in the support of A. And now here's a lemma. If, so claim, if elf psi is non-zero on just the piece of A that's sitting at this one guy, at this one B, right? So I just take I throw away everything else. If this is non-zero, then elf psi of A is non-zero. Okay? So why is that? So here's the sketch. So, okay, I can write down a fiber sequence. So I consider the fiber of A mapping to IB lower shriek IB star upper star A. So there's such a map because B is maximal in the support. Okay, and now I'll do a little bit of casework. So the easiest case is if elf psi is B is 0, then it's easy because then elf psi of A is elf psi of this IB lower shriek IB upper star A, and by assumption this is not 0. Okay, so then we're done. So the more interesting step is cases if elf psi B is not 0. Okay, and so now let's assume for contradiction that elf psi A is 0, okay, which we want to show cannot happen. But a priori it could happen, right? Even though it's non-zero on this last guy, what could go wrong is that somehow the elf psi on the rest of the support of A gives you something that for some weird reason kills exactly the stuff that elf psi maps the first, like the minimal guy to. Okay, and we have to rule out that can happen. Okay, so if assume this is 0, then something weird happens because then the Arhom of elf psi B to elf psi IB lower shriek IB upper star A is non-zero, right? Because I guess it's, well, you just look at the fiber sequence up here, you apply elf psi, then elf psi A vanishes, then elf psi B and elf psi I lower shriek IB upper star A are equivalent, maybe up to some shift. And so in particular, there must be a non-zero map. Okay, but this would be really, this looks really weird because there is no homomorphism from B to IB lower shriek IB upper star A. Okay, because the B is supported on the smaller things. And so they can just not be such a map by just the usual semi-orthogonal decomposition. So this map doesn't exist. And if we hope that elf psi is an equivalence, then this map here also cannot exist. So now we have to find a contradiction to that. And the way we do this is that after filtering, B and this IB lower shriek IB upper star A, we deduce that if an R-hom of the following form is non-zero, so some R-hom of the form L psi Eisenstein Q bar IBL lower shriek BL to L psi some Eisenstein for some P bar IBM lower shriek AM is non-zero. So what I'm doing here is just, I guess this B is supported on more strata, but I can filter it by just the things that are sitting on one particular stratum. And then on each of those, I can filter it further into supercuspals and so on. And then eventually, I'll use this property I have up here, this one. Okay, and this tells me that every representation on one stratum I can eventually write just in terms of Eisenstein functors of some parabolics. And that's what's happening here. Okay, and so this is for some Q is LU prime, P is MU, both are parabolics, and G, but such that the image of this BL and BG specializes to the image of this BM. Okay, but now I rewrite this using the Eisenstein compatibility as the spectral Eisenstein functor for Q of L psi L I BL lower shriek BL. So this BL, by the way, was assumed to be supercuspal. I'm running out of time, so I'll just say this. And I can also rewrite this as I spec P of LCM IBM lower shriek AM. Okay? But now both of these sheaves, by our assumption, are cuspal. Okay, but then we had this semi-orthogonal decomposition of these cuspal sheaves on intco of par G that was talked about on Tuesday, I think, by Teresa and Alexander. And part of that is, well, essentially what they're able to show is that the similar property that I have here, that is quite obviously true on ban G, also holds on par G, at least when I know that these things are cuspal. So Alexander and Teresa verify this R-hom is 0. Okay. So this is the first step. And now, so what does this mean? So as soon as I have as soon as I know that on the maximal as soon as I know that, well, I guess just from this lemma, it follows immediately that it's enough to show now L psi IB lower shriek is conservative. Oops, conservative for all B in B of G, right? Because it's enough to check now that these guys are non-zero, these guys here. And okay, this we do by a lot of casework. And since I'm running out of time, I cannot really say too much about this. So, okay, the first step one can make is that without loss of generality, B lies in the neutral stratum, neutral component. Of ban G. Okay, and how do you do that? Well, if it does not, then there will be some Hecker operator that shifts it there, because the Hecker operations are compatible with the central grading, and that's central, yeah. So, and Hecker operators are conservative, which is a really nice fact, because there's a dual Hecker operator, and if you compose them, then they retract to the identity, so it must be conservative. And so we can, via some Hecker operator, map it to the neutral component, and now it's a lot of cases. So let me just maybe mention two. So the first case is if B is 1 and A is supercuspidal, then, well, this is really the assumption B that is conservative here. And let me mention one more case, and then if you want to see all the glory of all these cases, then you can look at the proof. So maybe one more case is if B is not 1, but A is still supercuspidal at this, so it's a supercuspidal representation at this point IB, B. Okay, and then in this case, let P be as above, the dynamic parabolic of the Newton point. And then we see that this L psi IB lower shriek, renormalized maybe, is just L psi of I's P bar I B M lower shriek. So this was the formula that I wrote above. Okay? And then this I can rewrite now by Eisenstein compatibility. As this functor. Okay, but now I know that this functor here is fully faithful. And so the only thing that's left to check is that this guy is conservative, and it is, at least on the stuff that happens here. And this is again by Alexander and Hirohisa. As far as I know, they did not specifically mention this, but it should follow from their result that this is conservative, at least on this co-Porgy cuspidal sheaves that have the correct central grading. And I might mess up the signs here, but oh, sorry, par M. Yeah. Okay. So the vague idea is that, yeah, at these non-supercuspidal, at these points that are not equal to 1, I use some Eisenstein functor. And now, okay, there's the cases where A is not supercuspidal, and then you can do some more Hecker metric and some more Eisenstein functors. But roughly the ideas are similar. And that's all I want to say about this. So sorry for being slightly over time. Thanks.